Welcome back to Unit 16, Kinetics and Equilibrium. This is at the PreAP 10th grade chemistry level. Now, we were talking about factors that affect the rate of a reaction, and just as a brief, quick overview again, the first factor was the type of reaction. And this just gives us a little opportunity to review this from the very beginning of the year. Which of the following is considered a redox? If you have elements going to compounds, it's a redox, period. I'm going to go ahead and assign oxidation numbers so you can see that they changed, but elements are 0. In compounds, they have a value, and so that's automatically a redox. So here you have an element. Here the same element is in a compound. It's a redox. I'll assign oxidation numbers. I'm going to leave and just do the sulfate together there for now. And because we see that it didn't change, so I'm not going to worry about the sulfur and oxygen separately. Zinc went from 0 to +2. That's less negative. It lost electrons. It's oxidized. Hydrogen went from, +1 down to 0. More negative, it's reduced. So those are redoxes. This is not. We've got +1, nitrates -1, sodium's +1, hydroxides -1, and everything is still pretty much the same thing here. You can think of water in this case as HOH, and I'm just going to be very simplistic about it at this stage. The key point is that nothing changed oxidation. Lead is +2, nitrates -1, +1 -1, +2 -1. +1 -1. Everything stayed the same. These are double replacement. Double replacements are not redox. And so what we would find is that these two would be our fastest. You would see that beautiful yellow lead iodide form immediately, instantaneously. Here, you would start to see these bubbles formed fairly quickly, but it might not be quite as quick. Now, we are making some generalizations here, but as a generalization, the double replacements are going to be quicker. Now, let's move on to factor 2, and that's temperature. Now, temperature, in terms of a link with collision theory, does so on two fronts. It affects both the frequency and the effectiveness of the collision in the sense of the activation energy. Temperation, how did I do that? Temperature, sorry kiddos, temperature, okay? Both the frequency and the effectiveness of our collisions in the sense of our activation energy. Now, what the thought process is that an increase in kinetic energy, okay, means that there is going to be an increase in the frequency. They're moving at a faster rate, right? So you have an increase in the rate, which means you have an increase in the frequency of the collisions. For example, if you're in the hallway, if you're walking down the hall, you're not very likely to run into somebody. But if everybody started running down the halls, it would be every principal's nightmare. But you would also increase the frequency with which people are running into each other and hurting each other. Okay. Also, those collisions are going to collide with an increased energy. Right? So if you're walking down the hall and you bump into somebody, no big deal. You apologize. You don't start a fight. You just say sorry. You move on. Right? But if you collide with a lot of energy, then it's going to hurt. And there's going to be some real damage. In this case, more collisions will have enough energy. They'll have that sufficient energy to overcome the activation energy, to have an effective collision. Effective means they have enough energy to get up and over that hill. So you'll have more molecules with enough energy to get up and over the hill. The hill doesn't change, but instead of molecules colliding and coming back and colliding and coming back, they collide hard, and then they've got a better chance of making it up and over. There's my lovely artwork. All right. Factor 3. The first few we're going to do are pretty quick, so I'm going to run through them quickly. It's pressure. Pressure does affect the reaction rate, but only if we have reactants that are gases. Okay? And here's why. An increase in pressure, assuming we keep temperature constant, because if we want to look at the effect of pressure, we've got to keep temperature as a control variable. So if you increase the external pressure, if the volume can move, the volume is going to decrease until the pressure in is equal to the pressure out. And you notice in this picture, these molecules are much more closely spaced. So an increase in pressure will decrease the volume occupied. The molecules are closer together. So instead of you being spread out amongst the classrooms, here you're all clustered at the end of G Hall right by the stairway where people stop and run into each other all the time. Okay, so the molecules are closer together. That means there's going to be more collisions. And so you increase that frequency of collision. Not the energy per se, but the frequency. So when they're talking about effective collisions here, we're really talking about a probability. If there's more collisions, if you meet more people in life, you're much more likely to find somebody that you connect with as a good friend or in a relationship. So, to summarize, an increase in pressure means an increase in the rate because there's an increase in the frequency of collisions, but only if those molecules are gases. So that's 2 of our factors. In the next video, we'll touch on a few more, and then we're going to land on one of these 6 factors for quite a while and do some mathematics with it. So until then, this is signing off.